On the other hand, hydrodynamics is a good description of what's seen in the data. But as you know, hydrodynamic simulations, as successful as they are at the moment, they still need initial conditions. So in some sense, there's still a lot of interest in finding alternative prescriptions for specifying hydrodynamic initial data. So an alternative description, in other words, is still very interesting to people. So what we'll be trying to do today is to find such an alternative description. And with the advent of ADS-CFT, one candidate description is a merger of black holes in ADS, for example. So our goal today will be try to detail this particular candidate. So what we'll be trying to make is a model of heavy ion collisions using two black holes, and hopefully this model will only have a few tunable parameters. So in particular, the masses of the black hole, the boosts with which these black holes move towards each other, and the impact parameter. And hopefully the rest will be determined by just the gravity dynamic. All right. So before I move on, so what I'd really like to tell you now is what goes into these kinds of models, what you need to do to get something like this going, much in the spirit of what's been going on in the conference so far, just giving you the techniques. But before I do that, I'd like to just, I think it's good to just remember what the caveats are in trying to apply holography in this way to real-world systems, because in the end, the point of the matter is we don't have ADS-QCD. So, but nevertheless, I think today it's useful to just take the practical point of view that even though we don't have a gravitational dual for QCD, we could still try to model these real-world systems using a conformal field theory toy model. And the toy model we'll be using is the same one we've been using so far, all through the discussions yesterday. It's n equals 4 super young males, and here's the gravitational dual. And in fact, it's exactly this field theory that you've learned many years ago, or this past weekend, depending on who you are. And here's so we'll be interested in observables of this conformal field theory. And what I've written down at the bottom here, just for your reference later on, is one of the observables we'll be looking at after we've solved the gravitational dynamics. So it's just that covariant formulation for the one-point function of T mu CFT. And I heard that this is what you had studied over the weekend, so I just decided to write it down to make sure that you remember, because we'll be using this. It's the only observable we'll be computing today after we've solved the gravitational dynamics. All right, so let's just summarize before we go on, because after this slide, I'll have to ask for your a little bit more attention, because we'll be just going into the details of the equations, the methods we'll use. But before we do that, I just want to be sure, are there any questions in what's happened so far? But basically, it's just the motivation for why we're doing this, and just a general flow chart for what our approach will be. So in general, we're going to use ADS-CFT to relate, in the end, a classical gravity simulation to heavy ion collisions. And there's caveats going from here to there, of course, but nevertheless, that's the approach we'll be taking today. All right. Yeah, perhaps I should have done that, but I didn't know how to do both or something. But anyway, the main point I want to make is there are caveats. That please remember the caveats, because it's very bad to
You also didn't say too much about if you wanted to take like gravity, for instance, or higher. Well, this is really large and large lambda and all these kind of things.
Yeah, thank you. I would like to say more about that. I think I had a couple of slides. But anyway, the reason why I don't is I want to just focus on, in the end, classical gravity. And so the point that Bilke is making is, yeah, there are some limits that one has to take in this correspondence to ensure that classical gravity is the description that you have for these kind of conformal field theories. But let's assume we've taken those limits. That's the point of view. And I'm sure you've done this over the weekend, if I remember correctly, so I think it should be okay. All right, are there any other questions before we move on? Because it's going to get rather hairy. All right, good. Okay, so the first thing I'd like to do is to establish some notation for us. Okay, so there are many things I want to communicate to you today, and just to make sure that you have as a take-home message. One of the main ones really is to make sure that if you're not so familiar with anti-de Sitter space, that I want to go beyond just telling you, oh, anti-de Sitter space is a maximally symmetric solution of the field equations and negative culture. I mean, you've heard that so many times before. What I want to give you is a feel for the space-time, in the sense that you could almost touch it. So I want to give you that, something like that. So the way I've decided to do that is by this kind of picture, because it's sort of intuitive. So just think of this locus of points. Don't even think about space-time. It's just that locus where capital X is, some ambient space. It's a higher dimensional one, so I guess it's d plus 1, capital D plus 1 dimensional. Now, okay, so I should say that anti-de Sitter space is indeed a solution of the Einstein field equations, but you could think of it as, if you wanted the metric of ADS, you could reproduce it by taking such a locus point embedded in a flat space, as I just said, and finding the metric intrinsic to that such a surface. So, for example, just take this embedding, and you'll get the metric of ADS. Now, the surface, okay, so let's specialize the 5 dimensions for now so that I don't have to keep on writing down capital D. So I've described the surface in terms of 6 coordinates, but it's a 5-dimensional space, so clearly this is not a very efficient way of describing the surface. So presumably there's a way of describing the surface that involves only 5 coordinates. So let's do that. Let's pick that one. Let's pick these 5 coordinates. So t prime, z prime, x1, x2, x3. So it's one way, and these are defined by these embedding functions. But anyway, the point is, this is what we've been talking about all day, yesterday, and probably much more the rest of the week. It's the so-called Poincare coordinates. I wanted to show you this because really, on the end, they're just a choice of embedding functions from this point of view. So if you wanted to know what Poincare coordinates are, well, it's a certain choice of covering the space. In fact, it doesn't cover all of the space-time. It only covers half of it. So that's what I tried to depict with a shaded region there. And I'm going to keep this here because you might find it useful later, but we'll definitely find it useful later on in the stuff. So what if we wanted to cover the entire space-time? We haven't done this so far yet. I think all the talks yesterday, if I remember correctly, was more about this patch of space-time. So what if you wanted to do that? It turns out there is such a choice. So let's call them unprimed p r chi theta phi. And that choice of embedding corresponds to this choice of embedding functions. There's 6 of them. And these are the so-called global coordinates. You might ask yourself, why bother showing us all this? And by the way, these are the forms of the line element in each of these coordinates. This first one's probably familiar from yesterday. You've seen it already. The second one perhaps less familiar, but I'd like you to become used to it. And the reason is that today, as opposed to just sticking to either the Poincare patch or global ADS, we'll be switching back and forth between them pretty rapidly. So I'd like you to become familiarized with them. But this point of view is useful because it's basically just telling you that they're just covering some space.
R squared on the 3 sphere.
Yes, you're right. I'm sorry. Thanks for catching up. Yeah, sorry. Okay, so here's one visualization of anti-de Sitter space. So it's usually shown as a cylinder. This is global ADS, by the global anti-de Sitter space. The reason why it's a half cylinder in this case is what I've done is, remember the global coordinates were a time, which is going up vertically. There's a radius, which you can think of as going from the center of the cylinder to the outside, which is the boundary. And then there are 3 angles. I've just unfolded one of the angles and goes from 0 to pi. So that's why it's a half cylinder in this case. And the Poincare patch, which is that other half, is just shaded there in green. So what we'll be interested in today is not just pure ADS, but space-times that are asymptotically ADS. So what I won't tell you technically, well, okay, here, I think I did write down some of the technical details, but really all I want to, there are two things I want you to take away from this slide. One, an asymptotically ADS spacetime, roughly speaking, is pure ADS, but with, in the bulk, you allow other things to happen. But as you approach the boundary, you approach it in a very specific way, such that you recover just pure ADS. And the other thing I want you to take away from this slide is just the picture. And the reason why is what we'll be doing now is, I want to give you a tangible feel for what anti-de space is and what the dynamics looks like in that space-time. So literally what we're going to do now is take slices of this thing and evolve it in time. So that's why I want you to remember half cylinder, because here's a slice of it. And what we're going to do now is just, look at what a time evolution might look like in global ADS. So here what I've done is I've put, so this is, the system here is gravity coupled to a massless scalar field. So there's no potential term, it's just the gradients appearing. And I've initialized that scalar field, but this is the scalar field that I'm showing you here, not the metric. Such that there are two lumps, the Gaussian lumps, it turns out, antithetical points in global ADS. And again, to orient you, the radial coordinate goes from 0 here up to the boundary. So this literally is the boundary of ADS. It's at infinity. Just compactified it using compactified coordinates. And let me show you what the scalar field does. So it's coupled to the metric, but notice that it's very weak. So the scale here, so it's your 10 to the minus 4. So in other words, you could think of this more or less like a scalar field propagating in just pure ADS spacetime. So here's what it does. I'll simulate this for a time of pi, and you'll soon see why it's a useful time scale in global ADS. So it's well known in pure ADS that if you consider some point P in just pure ADS, so it's fixed, not back reacting, and consider all the time-like geodesics that emanate from that point, there exists an image point Q such that all of those time-like geodesics will converge. So basically what I'm trying to say is, if you have some point P in space-time, there'll be an image point Q such that all of these guys will converge. And in fact, Q has another image point as well, Q prime and Q double prime ad infinitum. So you just what you just saw is one part of that endless cycle. So what you saw is that, if I play it again, these Gaussian lumps, they disperse, of course, which is exactly what you'd expect from a massless scalar field. But the space-time is such that they will all reconverge at image points, at a time later of pi. So there is there's two.
The lumps are now at the image points. You put them deliberately at the image points of each other. No.
It doesn't really matter where I put them. The point is that wherever I put them, they'll actually, maybe I just did half. Sorry. I guess with that, if you wanted to go with that picture, you'd have to wait for one more pi until they come back, I suppose. Or maybe not. Actually, maybe this is correct. So it's, the image point's there, and what will happen after another time of pi is that these two will come back to where it used to be. So I guess in that case, there's only two points where they bounce back and forth with each other.
Okay. So
sorry, did that?
One of them is P, the other one is Q.
One of them's.
Where you put them? Did I understand that correctly?
Yeah, I suppose in this case, yes, you could say that. Let's see.
So they're just exchanging, I understand.
Mm-hmm. That's right. What did I? Oh, right. The other reason why I wanted to show you this particular feature of ADS, often you hear that ADS is a box. And in this is the sense in which it is. So this is a massless scalar field, so you see that as opposed to the asymptotically flat case where you would expect that massless scalar to just disperse up to infinity. You have boundary conditions such that they're actually confined to the space. So as opposed to that, I'd like to now show you what dynamics looks like on the Poincare patch. So you might think this is rather trivial because, and in some sense it is, because the Poincare patch is just a region of the full space-time. It's just expressed in different coordinates. But it's instructive anyway to see what evolution might look like in these coordinates for a similar sort of setup where you have a Gaussian lump of scalar field, for example, just dispersing. So the picture I suppose I'd like to give you is that in the Poincare coordinates, it's useful to take a Poincare patch like this, like where the boundary is the Minkowski space up there, the depth is the z prime that goes down into the IR, as we've been calling it. And all of the slices of the Poincare patch are hyperbolic spaces. So the reason I want to show you this is that in some sense, like heuristically, if you could think of global ADS as dynamics in a gravitational box, you could think of Poincare as dynamic. It's also a box in some sense, but it's a box with this big hole in the bottom in a sense that I'll just show you now. Big hole in the sense that this is where the patch ends. So if you thought of dynamics from the global picture, it would want there'll be dynamics, but the energy density would be moving in general out of the patch. And that's why you'll see from the point of view of the Poincare patch, things appear to be exiting the space-time, but really all it's doing is exiting the patch. So here's some lump of scalar again. I think I'm sorry, this is a metric component I'm showing you. But again, it was generated by considering initial data for a scalar and then just solving the initial data constraints to find out what the metric looks like. So it's some distribution, just to orient you, the boundaries of here, the Poincare horizon, which is the end of the patch, is down here, and this horizontal direction is one of the directions transverse to, it's just, you can think of it as one of the directions in Minkowski space, just one of the normal directions. So if I let this distribution of energy density go, so the reason there's some, well, okay, I'll let you watch it for a bit. There's some complicated dynamics going on, essentially because I've also allowed spatial variation in the slice is transverse to what I'm showing you here. And also changing the color scale. But essentially what I want to point out to you is that indeed most of the energy density appears to be exiting. But again, let me just remind you what all this really means is that it wants to try to exit the patch. And in Poincare coordinates, let me emphasize, it won't do that for a finite time. So this is compactified coordinates. In Poincare time coordinates, which is what the t that I'm displaying there, it'll take an infinite amount of t for this energy density to get there.
So it actually doesn't exit, right?
It does not. It looks like it is, but it will never do so.
That doesn't even look like that.
Oh, I stopped it. No, but the point is, yeah, you're right.
It falls down.
It falls down. The point is, though, if I re-express this in terms of global coordinates, of course it will exit the patch. I mean, it's just...
It's invisible boundary observers on the boundary of Poincare patch.
And this simulation you did in global coordinates and then you converted, or you did it directly?
I did it directly. There are reasons. This is why I'm showing you this. I want to show you what's, first of all, the dynamics, and second of all, I'll show you in more detail why is it useful not to just do the trivial thing and do essentially the Weyl transformation along with the diffeomorphism to just get some solution in one thing to the other.
But that wouldn't work, right?
It does, of course, but it's just practical reasons. From the point of view of the numerics and also from the point of view of, the numerics in the end is what it boils down to. You have problems with Poincare radius with some finite energy density everywhere. I think it corresponds to infinite energy globally. Because the volume rescaling is that right? My first impression is no, it's not right, because if I just naively did the biotransformation, I think infinite energy of the Poincare would probably be something biological. Is that? Well,
The volume of the boundary is infinite in Poincare, but it's Minkowski, and the volume of the boundary of Doubling is clear.
that's right.
Why?
Yeah, I haven't. Sorry, let me think about that a little bit more. But my first impression is no. Maybe you might do it.
Finite energies and for the theory on the sphere correspond to local envelope. Okay. One can invoke the operator state correspondence, which is suggested for understanding this right.
Okay. Sorry. I also just wanted to show you what the dynamics looks like in the transfer slide. So this is just. So I picked the constant z prime, and this is how the initial energy distribution that was set up there evolves time. Okay, so what I'd like to show you now is the form of the field equations that we use, because it's distinctly different from what we've seen so far. So far, remember, we've seen the characteristic form of the field equations in ADS. And what we saw there, as Vilka showed yesterday, is that the equations simplify to essentially a set of nested ordinary differential equations, which makes it very convenient to solve. We'll be taking the exact opposite approach here, in the sense that we'll not be simplifying the field equations at all, and we'll not be using any simplifying ansatz for the metric. So in other words, instead of defining new variables for the metric in a way, so for example, we won't be fixing a form of the metric, so we'll be using just the general, exactly what you would, just GTT plus all the other components. So no simplification whatsoever. And we'll be taking the full field equations and directly discretizing them. So there'll be a set of second order PDEs, 15 of them it turns out, all coupled together. So let's start from the vacuum equations, add some cosmological constant and a matter piece. So hopefully this is familiar to you guys. It's just a trace reversed form of the field equations. And the reason I write it in this way is it turns out that to get to the generalized harmonic form, it's much easier to do this, essentially because the generalized harmonic form just expands what the Ricci tensor is in terms of its fundamental variables, in our case, the metric. And the goal behind the generalized harmonic form, as the name might suggest, is to try to recast the field equations in a form that's as close as possible to a wave equation. So the reason for this is that, if you wrote down the field equations, for example, like this, it has no well-defined mathematical characters, PDE. And you need that in order to actually solve something. And one way to do this, and what we'd like to do is to cast it in a form that's hyperbolic. So in other words, like a wave equation. Okay, I'm sorry, let's just add a couple more terms. So you'll see in the exercises why these are important, but I'll leave it undetermined for now. So let's rewrite R mu nu in terms of its fundamental variables. So here they are. Again, you'll do this in the exercises, so I'm just flashing you the summary so that you have an idea what the idea is behind this calculation. So you're showing the exercise that R mu nu, in fact, is equal to this combination of the metric components. What I'd like to draw your attention to is that we're nearly there. We're nearly at the goal that we're trying to get to. We wanted a wave-like piece, and indeed, it looks like the principal part of this thing is the wave operator. But we're spoiled by, unfortunately, this term, for example. So that term is something we don't want. And what I'd like to show you now is how to remove it without removing any generality from the equations. So the first thing I'd like to do is re-express this so-called generalized harmonic constraint in terms of its definition. So what the constraint is, it's just a redefinition of, so it's really it's just a redefinition in the following sense. A solution of the field equations satisfies C mu is identically 0. So really, this is just defining what H mu is. It's just this particular combination of metric components.
So the action of blocks on X mu is defined in the SO X mu is a tensor.
Yeah, it's just my
H
shorthand.
mu is a new field.
H mu.
What if capital H mu is a new field?
It's a new field. So you're getting to something I want to say, which is that formally what we are doing is we're augmenting field equations to a richer system. But in the end, what we will do is, after we've gotten this richer system, we will restrict the solutions to only those that are Einstein.
What are N and P in capital?
Yes.
Symbols that they
Yeah, again, sorry. So this one, those are the terms that I'd like you to work out the exercises. But so kappa, p, and p are variables that are tunable by you and by yourself. And n mu is a normal vector, normal to slices of constant time. The reason I didn't talk about them so much is what I want you to show is that this piece of the field equation, what I want to show in the exercise, that piece of the field equations dynamically forces the C mu to be 0. So it's like it's a term that makes sure that you're satisfying the constraint that I want. The constraint, you're only having solutions with field equations rather than some other solutions with this new complicated set of equations. Okay, so let's just do that identification and then replace C mu by its definition. So really what we've done is we've said, okay, we're free to set the delta x mu to whatever h we want, and h is some new field variable. What that does, it turns out, is it cancels out a whole lot of terms, including the one we really don't want. And again, this is what I wanted to show in the exercises. What the heck is this thing that I wrote down in delta x, and what's its covariant derivative? So great, we now have.
So could you repeat which terms you wanted and the term you didn't want, why that one?
And the reason why is that it's not part of the, it's a second order derivative, so it's important, it's part of the principal part of the equation. But it's not the wave operator. So it spoils the wave. So it spoils what's called the principal symbol of your PDEs. So essentially, let me just say a few more technical details. So in order to have a well-posed initial boundary value problem, you need what's known as a strongly hyperbolic PDE. So there's three main kinds to where there's weakly hyperbolic, strongly hyperbolic, symmetric, and they get stronger as you go. It turns out that a necessary condition for that, what we want is that it's strongly hyperbolic.
Another thing is probably if you have that term,
Yeah.
you haven't completely gauge fixed your coordinates, right? There's still some coordinate freedom which you should fix, otherwise you're just going to run problems.
No, this is just at the level of PDEs. I haven't fixed any coordinate degrees of freedom yet.
Well, that's in its age, right?
It is, that's right, but I haven't specified what h is yet. So until I do, I have not fixed anything. So for example, when I set if I set h to 0 identically, then that's what's called harmonic coordinates, that's choice of coordinates. But before I do, it's just something. It's just like a new dynamical variable that I've included in my augmented equations. So that's the sense in which I was trying to say. I'm taking the complete opposite point of view. I'm giving myself a harder problem. I'm giving myself a harder problem and seeing that it simplifies things later, rather than simplifying the problem and then just solving a simpler set of equations. That's sort of the philosophy, I suppose, of Western models. And again, the motivation for the philosophy is at the level of the PDEs. We want PDEs, a set of PDEs with good properties. Okay. So this is what I wanted to show. You will do it, so don't worry if you didn't catch it. And incidentally, you could check. This is solved by the pure ADS metric, for example, or really any solution of the field equation. as long as C is 0. So again, this term is just to dynamically make sure that that's the case. It's for any solution, C is always going to be 0. Good. Okay, so what do we do with these things? Given the generalized harmonic form of field equations, we don't introduce any auxiliary variables. What we do is we just take that as it is and directly discretize. And I'm sure you know exactly what that means. It just means that, for example, if I had a second time derivative for the metric component, let's say the t-teeth component, then I just take some whatever order finite derivative. So for example, just you know exactly what I'm talking about. It's just centered second order stencils. And we'll just directly discretize that. So what you end up getting are 15 equations. They're all coupled, and they're 15, one for each nu and one for each nu. Okay, before I go on, let me just say one more what I think is a very attractive feature of these equations, which is that in general, if you write down the field equations, it's not guaranteed. You have to figure out which equation it gives you, because an evolution equation is essentially, in the end, a rule for telling you how to evaluate any given metric component, given some data from an initial time slice at the next time slice. So it's just a rule. But if you write down the field equations naively, you have no idea. So let's say I wanted the rule for the t-teeth component of the metric component. A general writing down of the field equations, you have no idea which equation is going to be that rule. In general, it's going to be some combination. Some combination of those equations. What we've done here, as you see very clearly from just the form, especially the first term, is that the mu-nuth equation in the generalized harmonic form gives you the rule for the mu-nuth component of the field equation. So it's a very clean sort of decomposition. It's literally just the wave equation for each metric component. So okay, if we discretize that, let's say, and I've schematically described it as this new grid function. So for every grid function f, there's some operator, some discretized now differential operator L that's a function of the 4 spatial coordinates, now the grid points I, j, k, l, and of time. And again, let me just emphasize, we're seeking solutions that are Einstein, or rather, the solution of Einstein. Okay, we have 15 such equations. How do we solve it? So there are many ways, and I will now talk to you about a way that was described yesterday, but very briefly. So we're solving, again, these are not linear equations anymore, as opposed to what we had before. We had a nested structure of linear equations. That's very nice. We could do all sorts of things with that. But now we have to solve it somewhat more generally, because we have 15 coupled differential equations, and they're non-linear, each of them. So the most one scheme to do this, and it turns out to work very well, is the so-called Newton-Gauss-Seidel. It's really just the Newton method in the following way. Maybe I'll just skip to the Newton method part. You could probably recognize that bit. It's just the Newton method, literally. But you just have to do it at every grid point. So this is evaluated at every IJKL space-time location. And then it gives you the rule that goes from time step n to time step n plus 1. But that's too fast, because to have this kind of scheme, it turns out that you need three time levels. And you could probably see why, because, for example, to evaluate time derivatives, you definitely need 3 time levels. So what you do is, let's take for a given now, because we're going to be talking about initial data just now, but not quite yet. So at any given, let's say we had initial data at some point down there, and we're at some random time step. So what it does is, it requires data from Tn, and it'll take data from Tn minus 1 to Tn plus 1 as initial data. But at a general time step, you don't know what Tn plus 1 is yet. You only know Tn and Tn minus 1. So the entire idea is to set up an iterative procedure such that given data in these 2 time slices, you now have the rule to get you to the next time slice. So this begs, of course, the question, how did you get the initial time slice in the first place? Because you need to start this procedure somehow, right? We now have a rule for how to do it, but we need to initialize this.
So you have to do this Newton iterative scheme because you're saying you're using an implicit time stepping, right? You could also just explicitly time step, and then everything will be much simpler.
It might. The reason why we use implicit, I suppose, is that, well, it's easier to implement in the end. And also, it's, in some sense, in some cases, it's more robust. So we could use RK4, for example, and we're hoping to do that at some point. That in fact, would give us better convergence properties. But at the moment, it's just a scheme.
So it's easier to implement? Normally, if you just have the metric and the time derivative, you can just
the reason
look
it's
up in the equations.
So RK4 is harder because you'd need more than 3 time levels, right? So you're probably going to need 5, especially to initialize.
Well, that, okay, for the initialization, but you were just talking about time stepping at some point.
Mm-hmm. So yeah, I see your point. If you have an explicit scheme, you have an explicit expression for going to the next time step instead of iterating.
So, well, I guess the question, did you try that? I mean, is there a difference in performance, or how long does it, how many iterations do you need? You probably need only 1 iteration, right?
A couple it turns out, maybe 5 at most. But because of that, you see, iterative schemes get very expensive if you need more, like a dozen or more every time.
But also, computing a Jacobian is much more complicated than computing just equations by themselves, right?
That's right. But on the other hand, we don't really. So we hard code what the Jacobians are, given what variables we have. So we don't actually have a numerical way of computing. That would be very expensive. But it turns out we have a cleaner way of doing it. So it turns out to be a somewhat efficient scheme. But you're right. I mean, RK4 anyway is in our to-do list. So we know for sure that that's something that will probably help things.
Yeah, we always just explicit time stepping.
Mm-hmm. And anyway, the main reason I wanted to show you this method is it was mentioned yesterday, and I don't know if anybody talked about it, but it's just good to have on the board so that people know that it's actually used and it can be useful.
Do I understand correctly that with this method you need to have 2 initial, like the initial value problem needs to be specified at 2 time slices? Because you need 2 slices to update?
Yeah.
Okay.
Okay, I'll talk.
And you need 1 slice per derivative, or what fixes the number of slices you need? Is there a physical intuition? Why you need 2 slices, not 1? Because usually I would assume 1 is enough.
You need the metric and the time derivative.
Yeah, so
1 per derivative.
So it depends on the order at which you want to so the order of accuracy with which you want to initialize your data. So you're right. If I wanted to initialize it to first order, accurate in time, I could use just 2 slices. And the intuitive, I mean, the actual way to think about this, why, like with 2 slices, you could get a first order accurate representation of what the derivative is. If you have 3, then you could do the centered thing, which is the centered stencil, which would give you second order accurate scheme. The more accuracy you want and find a different scheme, the more you're going to need.
So does your time evolution have some instability related to hydrodynamic instability or something, like Coulomb, Cauchy, some condition?
Oh, is that hydrodynamic really? Yeah, so that's not, that's just the
hydrodynamic, but
that's just causality. So
yeah, causality problem, yeah.
Okay. Yeah, okay, good point. I wasn't going to say it, but might as well. So by causality, as Takaki's pointing out, let's say you had grid spacing delta x and time spacing delta t. Then you're going to want, just by causality, and we're going to use units where speed of light is 1. Okay? This spacing, let's define it as the Courant factor, the CFL, Courant Friedrich Louis factor, lambda. Let me do this bigger because I'm sure no one's. And typically, the way people put constraints in this lambda is to do the so-called von Neumann analysis of the linearized system to try to figure out what stability condition you need. Typically, what people find for very simple systems is that lambda has to be just less than 1. Let's say. So it's going to be greater than 0, less than 1. So in practice, and maybe this is what you were getting at, like typically what people just do is they make it a small reasonable number, such that you don't want to do such an expensive time step, because the smaller lambda is, the smaller your time step is going to be, the more expensive your simulation is. On the other hand, if you make it too large, you're going to get into the unstable regime, so you kind of don't want that. Thanks. No, so we don't. We keep lambda. I think my lambda is typically around 0.1, 0.2. Any other questions? All right. I think what I wanted to talk about was, to follow up on the questions so far. Yeah, how do we initialize this sequence? So here's just a graphical depiction of what it is. Essentially, what we need is we need data for the metric and really all of the other field content. So for example, if we had a scalar field, we need the same for the scalar field, but I've just written out a metric there. We need that, the profiles of metric and other fields on the initial time slice. Let's call it t equals 0. And we also need time derivatives at t equals 0. So how do we do this in particular is what I want to show you now. So here's the way I specify it. Unfortunately, I haven't shown you the equations because, again, I want you to work this out with exercises since we have time this afternoon. But it's the so-called conformal decomposition of the field equations that we'll be using. So usually in the asymptotically flat case, what people have found useful is to constrain yourself to just initial data such that on the initial time slice, the intrinsic metric is just conformal to the metric of flat space. So it's just called flat. So what we've done in this asymptotically ADS context is just do the obvious generalization and just ask. So again, this is a restriction of initial data. So restrict yourself to data such that it's spatial, that the intrinsic metric in the t equals 0 slice is just conformal to pure ADS. Two reasons why this is useful. You know exactly what pure ADS looks like, given some representation of choice. And it turns out that what this does is it turns 5 coupled elliptic nonlinear differential equations into just one. And it's one equation for this scalar. So basically you just have one equation that you have to solve, elliptic. It's nonlinear, but it's easier. So that's essentially what I've done here. So you see, once I've solved that equation, I have a zeta. Plug that in and you know exactly what your metric is. So now you have a couple more choices to make. So that's phrased in terms of lapse and shift here. You could rephrase that in terms of slicing conditions. So in terms of, for example, the trace of the extrinsic curvature of your initial surface. And maybe it's, and other things. So for example, maximal slicing will give you, I think that's 0 trace and something else about the extrinsic curvature. I can't remember exactly, but that gives you a differential equation for alpha. And in general, you'll also get an elliptic equation for the shift beta. What we do here, however, is we're going to choose time-symmetric initial data. So for example, the time derivatives are all 0, and that turns out to severely constrain what shift and alpha you want. And in fact, we could choose the shift to be 0 and the alpha to be whatever we want at this point. And again, remember that the initial data will also involve this generalized harmonic functions, HB. As Vilka pointed out, it's the choice of coordinates in our case. And in this case, it's very simple. What is the initial choice for HBU? It's exactly what we had chosen up here, but evaluated given that constraint. Is that clear? Because that could be very confusing sometimes. Because in the end, what I've done here in the slide, it might not have been obvious to you. I've mixed the ADM formulation with the generalized harmonic formulation. The point is that they're both equivalent to each other. So you could phrase any problem in terms of one or the other and just translate. So what I've done here is phrased it in the ADM language and I'm just converting it to generalized harmonic later on. The reason being that in this context, ADM is actually more physically intuitive. Okay, so how do we do initial data? And again, this is something you'll be working on in the exercises. So the initial data, the constraint equations for general relativity, as was pointed out yesterday, I believe. I mean, you're not free to just choose any old data on your surface. You have to satisfy these constraint equations. So what we do in practice is we are free to specify something. We're free to specify matter content. So we specify whatever matter we want, whatever profile we want with time derivatives. So that's the scalar field in the case I'll be showing you today. But once we have that, that will specify sources. J, that's the matter momentum density, and rho, the energy momentum density. So that's now sources for these constraint equations. And the rest of the equations involve metric components. So the game now is, given those sources, matter sources, what is the metric that's compatible with them according to the field equations? And what you'll show in the exercise is that these field equations are nothing but the Einstein field equations projected onto your initial slice. So okay, I'll let you do that. And instead I'll just, again, just discretize things. So notice that with our time symmetry constraint, so time symmetry incidentally means the extrinsic curvature of your initial slices, all of its components are identically zero. So that shows you that the second equation is trivially satisfied as long as you have no momentum density in your matter. That's very easy to make sure that you don't have. So we automatically just eliminated four coupled elliptics. And what we're left with is the top equation, the Hamiltonian constraint. And as I told you last slide, that boils down to, as long as you pick conformal initial data, that boils down to one equation, and it's the equation just for your zeta conformal factor. So that's what I've written down here. So this guy's just my symbol for the discretized version of the nonlinear elliptic equation for zeta. And if you're curious what these symbols meant, so this is the matter density, matter momentum density, and the extrinsic curvature in terms of the unit normals, the constant t slices. How do we solve it? I'll also present it to you, but it's multigrid. So multigrid is this method where it's very technical, so perhaps I won't go through all the details, but essentially two points I want you to take away from this slide. One, it's a method for solving elliptic equations. It's very efficient. Two, why is it efficient? The reason is that elliptic equations, when are elliptic equations inefficient? They're inefficient when you have, let's see if I get this right, short length scales. Very, very fluctuation-like short length scales in your problem. Because what elliptic equation solvers do is they typically solve the elliptic equation by a relaxation. And relaxation is very inefficient when, it's very efficient when you have long wavelength features, but as soon as you have short wavelength features, it still converges most of the time, but it'll just slow down a lot. So you'll need a lot of iterations just to resolve that. So what multigrid does is it'll solve the full equation in your normal grid where there's large fluctuations. So let me try to depict it here because I think it will be easier if you saw it. So let's say you had a grid and you had very, very large fluctuation and you had a normal, some mesh spacing. So what mesh refinement or multigrid does is it'll solve it first in this grid, but then it'll look at finer grids and then solve the problem again and then do interpolation again. And then finally, the point is that from the point of view of a finer grid, this feature, if I blew it up, suddenly looks like a long wavelength feature. Is that clear? So that's why it's useful. And this is how you do it. It's like a V-cycle sort of procedure where you descend into the hierarchy and then you go back up via extrapolations and interpolations. Okay. All right, so here's the hopefully halftime summary. Is it halftime? Okay. Here are the key features that I want you to take away. And so the first three the first two we've already talked about, and again you'll be looking at the details in the exercises. The third one, you probably have no idea what the cartoon method is because the name does not indicate at all what it's for. But again, in the exercises, I want you to work it out and just understand what it is. In the end, all I'll say for now is that let's say we had these full 4+1 simulations we're able to do, but we only wanted to do head-on collisions for now, let's say. How to do that in an efficient way? Well, the idea is that, let's say you wanted head-on collisions, and let's say that the collision axis is transverse to x1 and x2. That means that you have a killing vector in your spacetime of this form, such that all of your matter fields, or all your dynamical fields, satisfy this constraint. So for example, that's the metric, and this would be the scalar field. So it turns out that this constraint, you could work it out, and that's what I want you to do in the exercises, but intuitively you can already see what it's doing, right? Let's say you only considered the x equals 0 slice of this spacetime. The fact that you have rotational symmetry tells you that all of the interesting dynamics is encoded in the submanifold at x equals 1. And you don't have to simulate the entire thing. You could just simulate at, x1 equals 0. You could just simulate at x1 equals 0, and then in some sense rotate the entire solution to get the rest of the thing. So it's just telling you that the dynamics of the full manifold is just encoded in a submanifold. And this is essentially what cartoon method does. It just says that we're going to not impose the symmetry in the usual way. So the usual way people would impose that kind of symmetry is to write down a particular form of the metric and then write down simplified equations. We're not going to do that for the reasons I've told you already. Instead, we're going to solve the full equations, but we're going to impose the symmetry after the fact in this clever way, which turns out to be a more efficient way. Okay, so now what I'd like to just, I really want to show you the black hole collisions now, but before I do that, let me just, with black holes, you have the problem that you typically have dynamical horizons. How do you keep track of them? I want to just give you a brief idea. Mostly because there are actually other methods of doing that, and I'm curious to hear what others do. We have the mesh refinement, which is a great speed up for us, and I'll just give you a brief idea of what's going on there. And finally, just gauge choice in ADS. So if it wasn't clear already about h mu, what's going on there and how do you specify gauge choice, I want to clarify that in those slides, just to make sure that you have a very clear idea of what generalized harmonic means, harmonic gauge choices mean, especially in the context of ADS. So here's a busy slide. The reason why I show this to you is just to remind you, let's see, I want you just focus on the Alford null expansion for now. So this is the quantity that you can compute along hypersurfaces of your spacetime, such that if you find a hypersurface where this capital theta becomes negative, then that's a trapped surface in your spacetime. And we're going to make use of this to find dynamic horizon. So that's the main quantity we want to compute. But aside from all the details, let me just give you the general idea, or the general tutorial idea. So let's say we had a space-time at the Poincare patch, let's say. And we want to find out if we have a horizon in this space-time. So there's two things you could look for. So you know that there's all sorts of topologies that are possible here. Let's look for two things, either planar or spherical. Let's actually just look for spherical. So spherical horizons, what typically you do is to look for horizons, you start with an initial guess. So you try to make that as large as possible. And the reason is that what we want to do is to flow. So as soon as we have an initial guess, we can evaluate what theta looks like on the surface. And presumably, if it's large enough, what we'll find is that at every point in this initial guess, theta plus is greater than 0. So notice our dynamical equation for theta plus. So what's our h now is the radius of our, putative apparent horizon, and we're trying to evolve that radius according to the theta pluses we find in our guess surfaces. And lambda here is just some imaginary time, so it's just the parabolic time that we're evolving in. And notice I've constructed this parabolic equation such that, actually wrote it down somewhere here. If theta plus is positive, which means that we're not on the apparent horizon yet, but it's somewhere inside, the R decreases. So basically, if we're outside, this entire surface would start evolving to surfaces that hopefully will start finding any surface with a theta plus that crosses a zero if it exists. And if it does, and it eventually finds it, then we say that that's our apparent horizon. So that's, in words, that's what's going on here. These are just the details for how we do it. So we define some level set function, capital F. And from that level set function, you could, well, first of all, you have the normals to your time-like slice. And you have your space-like normals on the space-like slice. And given those, you can compute outward null expansion. And given that, you could evolve this parabolic equation, define your apparent horizon in the way I just described. Is that clear? Are there any questions about it? Okay, cool. Oh yeah, here's the picture. Actually, I forgot I showed you this.
So basically, you have two options. Either you find the apparent horizon, or it never stops.
Or it never stops. Yeah. So in fact, what happens is if it doesn't find an apparent horizon, it'll just collapse. So I have just a piece in the code that says if the radius that R capital RH becomes very close to zero, then it'll just say, oh, I'm sorry, I didn't find anything. Because eventually, what will happen is if it doesn't exist, it'll just keep on collapsing down.
So what happens if the horizon has disconnected topology? The thing that you start off with has connected topology.
So it has disconnected topology. I guess the way I'm thinking of that is two horizons, exactly. So what we do is, so that's what I'm going to show you. You need that for black hole coders. So we search for them independently. That's the answer. Okay. So we don't have one.
So you lasso each.
That's a great way to describe it. So, thanks.
But yeah, you can also miss it then, right? If it strings to a point, it might be there and you just missed it.
Yes, that is possible, but only if, okay, I'm trying to think of how that's possible. If I had insufficient resolution, I can imagine that happening. But what did you have in mind exactly? So if you had, did you have it disconnected the whole
I mean, this t equals 0 is not really a local condition, right? It depends very much on the positive thing. So you can, the apparent horizon might be there, but theta might not be 0 because of the curvature at that point. So it might go through the apparent horizon.
Yeah,
it's really there.
You know, I know, I'm pretty sure the answer is no, but I don't unfortunately have a theorem I need to tell you that. But there are some.
I'm pretty sure it could happen, but probably not in your setup. Well, maybe not in general.
I'm trying to think how you might miss it, because so I searched for it pointwise.
There's no local condition. It really depends on the complete curve.
Mm-hmm. Yeah.
If you find it, it's there, so that's fine.
No, I mean, I'm almost certain the answer is no. You can't miss it. But unfortunately, I can't make that more rigorous at the moment. Maybe when I can, I'll tell you. Yeah. What did I want? Oh, right. So here what I've done is I've just taken a special case. So here's global ABS in spherical symmetry. So instead of what Wilke was describing, which is that indeed the theta depends on what surface you pick to evaluate it, in spherical symmetry you know exactly what surfaces you need, because in spherical symmetry the only surfaces are spheres. So here what I've done is I've done something that usually you can't do. You can't usually display the profile of the theta plus, but here, since we know exactly what the surfaces are, I just fix the surfaces to be spheres and then show you what theta plus looks like evaluated in those surfaces. And you can see in this case that this features an apparent horizon. It's the red band here, where the theta plus dips below 0.
Theta plus is just theta.
Yeah, sorry, theta plus is just theta. I think I forgot to put the plus in some cases. Okay, a few words about adaptive mesh refinement. So we use, what do I want to say here? So first of all, the reason why adaptive mesh refinement is useful in relativity, particularly for black hole simulations, is that there are different length scales of the problem, and in some sense, the smaller length scales are not space-filling, as they might be in certain applications. For example, in hydrodynamics, you might find that you have small features everywhere. In the cases, in the spacetimes we're interested in, typically the small scales are the black holes, the small black hole participants themselves, and they're usually very well separated, and those are the only parts of the grid that you need to very well resolve. And large parts of the grid can be left coarse, like in this example here. So that's why you get a large amount of savings computationally. And the type of adaptive mesh refinement we use is this Berger-Oliger algorithm. And essentially the three main features I just want to emphasize to you. The first one is very important. The hierarchy consists only of uniform grids. And the reason this is important is that the implication is that if you had a code, for example, that only works without adaptive mesh refinement, that only works in one grid, then the Berger-Oliger algorithm just works on it directly, because all it needs is an algorithm that knows only about one grid. And what it does is then the finer grids, wherever you need more resolution, it will put down a higher resolution grid and evolve that, and then use interpolation or extrapolation rather to go back to the original grid. And the evolution is recursive. So in some sense, instead of evolving all of the grids, one way you could think about doing this, now that you have this hierarchy of coarse grid and finer and finer and finer, to obey the condition that Takaki had mentioned about stability, the CFL condition, the finest grid for sure, you have to evolve at a smaller time step, according to the condition we'd written down earlier, which is that the time step, it has to be proportional to the mesh spacing. So you could imagine evolving all of the grids with that small time step, but what the Berger-Oliger algorithm does instead is the coarsest grid, it'll evolve according to the time step set by its coarse resolution. So it'll take one time step in that direction. So let's say taking one coarse time step. And then the next step would be, at the finer resolution, we take 2 time steps. And then the next finer, we take 4 to get to the same physical time, and then so on and so forth. So in some sense, we make the most efficient use of our computational resources instead of evolving all of the grids with this finest time step. Okay, that's all I wanted to say there. Finally, I'd like to just remind you about gauge considerations. So again, remember, as we had pointed out, specifying a gauge in generalized harmonics amounts to specifying an h-mu function. It's this new field variable that we've included to enhance the field equations. And again, we've included terms already, as you'll work out later, to drive this h-mu to what it's supposed to be in order to get a constraint that gives you solutions of the Einstein field equations. So things get a little bit more involved in ADS, essentially because your choice of h-mu is not going to be completely arbitrary. So to make things a little bit more concrete here, let me try to use the example that was brought up earlier. So what if we chose h-mu equals 0 in this case? So let's see what the consequences of that are in ADS. Okay, to see the consequences, let's first remember, in ADS we have boundary conditions. And the boundary conditions can be set like this. So we've redefined our field variables in the way that was talked about yesterday. Instead of evolving the full metric, we're going to evolve this G bar metric, for example. So we've already factored out the ADS piece, and we've factored out one factor of the fall off. So Q equals 0 is the boundary, such that the G bars will fall off linearly. So fall off is Q, near Q equals 0. And now let's expand each of these variables and power series around q equals 0. So again, first of all, if this goes off as q, and I'm going to put a subscript of 1 denoting the fact that this is the coefficient for q, and so on for q squared and q cubed. And let's look at one of the field. So this is a schematic way of, remember, the t-teeth component of the field equations in our formulation gives you the rule for the t-teeth component of the metric. So this is just my schematic way of showing, okay, this is the field equations, the t-teeth component of the field equations. And if you expand that, you find that you have an expansion in q, and you have, the first term goes as 1 over q squared with this coefficient. So okay, let's try what we had suggested. What if we picked a gauge where h is 0? Then we find that if h were 0, either this component, the GQQ component, the first coefficient has to be 0 in order for the field equation to be satisfied. Or the first component, t-teeth component, has to diverge, or it has to become non-regular in the evolution. Is that clear to everyone? Because if this were non-zero and this were 0, then you have something that's diverging very badly near the boundary, and imagine you're evolving that. So eventually, what you'll get is a very non-regular representation of your t-teeth component. So either if one of those situations happens, basically what's happened is that you're no longer, it's no longer consistent with the fall-off conditions that you had assumed in the first place. So it's an inconsistent choice of gauge. So basically, it's telling you that your choice of gauge in ADS has to be guided by the asymptotics of ADS. So in this case, actually, you could probably already, you can see already what the consistency condition is. It's just that you want your choice of gauge such that it's tied to one of the metric components. So again, this is exactly what a gauge choice is in generalized harmonics. It's a constraint telling you what the h's are in terms of the metric. And again, according to its definition, all you've done is you've set a constraint amongst metric components and their derivatives. Is that clear? Great. Okay, so
of a peppermint Graham solution to the Einstein field equations asymptotically near the boundary to determine h bar in terms of g bar.
Yeah. No, that's exactly it.
You do this analytically for
That's exactly it. Actually, what I wanted to show you, and I forgot to do it, is that you do the same procedure you do exactly the same procedure for global ADS and for Poincare, and it works. So it's a general procedure. For example, if you added more matter, it's the same thing. It's just a general way of finding a gauge that's in this general context of generalized harmonics that's consistent with stable evolution. So you don't, in some sense, you don't have to guess anymore and just hope that the gauge choice again is a good one. Okay, how are we doing on time, Matthias?
Got about 20 minutes.
Oh dear.
Or 15 rather.
Okay, let me do this quickly. Actually, this is one of the main points I wanted to do for you. So I wanted to give you some intuition about just black holes in general, and also collisions. But okay, let me do this quickly. So what I've showed you here, okay, let's begin with, instead of going to collisions straight away, I just want to show you black hole, just a single black hole in global ADS first. And we'll do the same for Poincare. What I'm showing you here is one of the metric variables. It doesn't really matter what chi means. It's one of the coordinates. Again, this is in global ADS, so you see that the boundary is the half cylinder. And to orient you, again, here's the boundary. And what I've done is, so again, this is initialized by scalar field initial data. But this is the metric, after we've solved the initial data equations that you'll work out in exercises, this is what the profile looks like for this particular metric component given a Gaussian, a deformed Gaussian initial data profile for the scalar field. And I've made it strong enough, so look at the scale here. This is pretty large. So order unity is what you should be thinking of as just rather small. And a black hole forms immediately. So there are a couple of things while this thing rings down quasi-normally. Let me just tell you a few things that I haven't told you yet. We use excision to to evolve our black hole spacetimes. And what excision takes advantage of is that once you find your apparent horizon, you're assured that the characteristics within your trapped region are all pointing inward. So in some sense, as long as you're inside the trapped surface, none of that data is going to come out. So what we do with our excised surfaces is we don't excise right at the trapped surface, we excise at some point interior, just to make sure that we're satisfying that property. So that's what happened there. And so you see after, I don't know, 24 divided by pi is probably 8. So after about 8 light crossings, this thing is pretty much circularized. Okay, and here's just a quick look at what happened there. And you should be concerned now in some sense, because, so what I've showed you here is that, so here's a projection of one of the metric components onto a spherical harmonic. And the dots are the data, and the straight line fit is a fit to the quasi-normal mode frequency. It's this one. It's this quasi-normal mode frequency for this particular mass of black hole. So I'm showing the mass, the proper aerial radius as in units of capital L, which is the ADS length scale that's related to the cosmological constant. You should be worried because even though I showed you a presumably highly dynamical simulation or highly nonlinear simulation, apparently it's described by quasi-normal modes right from the beginning. So that's strange. So in some sense, this is in line with what we've been seeing before. Somehow, it's very, in this context, it's very easy to get into the linear regime, but what I'd like to show you with black hole collisions, and our motivation for doing black hole collisions was, we wanted to get away from this regime where the entire evolution is just quasi-normal modes. We wanted to see, can you get, as Chris was talking about earlier, yesterday, can you get a sizable and finite time where you have, that he labeled nonlinear, and then study the dynamics there, and then see the transition to quasi-normal modes.
Lots of CFT one-point functions.
I do. It'll be later on, and it'll be Ruby. Yeah, I think I might have something like a, so here's the end state. I'm sorry, I should have showed you the actual one-point function.
Because it's when you evaluate on the boundary, right?
Yeah. So this is on the boundary now. I'm sorry.
Huh? It's directly related.
It's directly related, but in some sense it's like process data. I wish I should have gotten some more raw stuff. I'll show you some raw stuff later, but it's in the proper batch. So this is already processed.
Question, please. What's the quasi-normal mode? Is that what you extract from this? Or sorry, I missed that. Or is that what you computed separately on the previous slide?
Yeah, it's what we extracted, but what we checked later on is that the frequencies match what you expect.
To how many digits?
I don't remember, to be honest. I actually don't know. I'm sorry. And there's one, by the way, caveat here, which is that usually in the perturbative calculations of quasi-normal modes, there's a particular gauge fixing that's been done to. It's been done in a particular gauge. Is basically what I'm saying. And we didn't try at all in that early study to try to match the gauge that's used in those perturbative studies. So basically what I'm trying to tell you is that it was done in a slightly different gauge, so there might be some issues there.
So this is global. And you're saying, okay, so there's only because in the Boulder patch there's no gauge choice as far as I'm.
You're referring to RH, so you plot it as a table as a function for RH over L, right? That's the gauge choice you're referring to.
No, I'm talking about how you represent the metric perturbations, for example.
The frequency should be independent of how you represent it, right?
Used in flat space or in non-compact spaces.
You can rewrite them in terms of gauge invariant fluctuations.
Yeah, exactly. That's what I mean to say. So we did not. That would be the best thing to do. If I somehow wrote my variables that I use to extract the quasi-normal modes, if I use variables that were gauge invariant, that would be great.
But in some sense, I think it matters less, right? Because if you imagine making these gauge invariant combinations, they're just going to be sums of, pick a shear channel, a transverse channel, whatever representations of the whatever symmetry you still preserve. And I think they're gonna, anything that's in the same channel will fluctuate at the same frequency.
Yeah, it's like coupling two harmonic oscillators to each other and then asking what's the frequency, eigenfrequency of a single one of those. That doesn't make any sense if you computed the eigenfrequencies of one of those, then you have all the eigenfrequencies.
Okay. Well, in that case, that's probably why we got very close to. Unfortunately, I won't be able to tell you how far we were from the actual.
No, that's fine.
What was I saying? Right, I'm sorry. So I had processed that for you.
Okay.
So this is now on the boundary. What I did here was I took what the TMU CFT components and I've reconstructed an energy density out of it. And I've done one further step. So instead of the energy density on the S3 boundary of global ADS, I've actually done the Weyl transformation to get it to the Minkowski piece of the boundary. And just to to make more contact with what you might expect as a model of heavy ion collisions. So that's the conformal factor W. And here's what it is in terms of the Minkowski coordinates. And what you find, and this, by the way, is the beamline, this is X2. So this is just, remember, one black hole, and it is a model for the state just after collision, and then sort of expands. And what you see is roughly what you expect, that you have more energy density flowing out in the beamline, what we're calling the beamline, and energy density eventually subcomes. Okay, so again, the idea now is we want to get away from this regime where it's completely described by quasi-normal modes. And the way I'm going to be quantifying it here is in terms of how close we are to hydrodynamics, which I haven't showed you yet, so that's why I want to show you now. But first of all, here's what a black hole collision looks like in global ADS. So there's a couple of things point out. First, remember, we're excising interior to the trapped surfaces, so the excised regions there are not exactly where the trapped surfaces are. The trapped surfaces are larger. So when you see things suddenly jumping, it's because the trapped surfaces did touch. It's just that the excised surfaces did not, because they're interior. The second thing you probably noticed is that there's this other black hole in the middle. Yeah, so the reason that's there is that in global ADS, it turned out we found it convenient to use spherical-like coordinates where we have a coordinate singularity essentially at the origin. And there are many ways to avoid this. One way is just to put a black hole there, and that's what we did. So we have here's another simulation. I suppose what I wanted to show you here is that you could make the regulator black hole in some sense smaller, but essentially it's the same sort of setup. And I evolved this one for a little bit longer because we're going to need at least a pi of time to extract out the quantities we want for a full cooperating patch slice. And so it's actually 2 pi, but the thing is we want to go from 0 to infinity, so it's just pi. Okay, so there's pi. All right, so we take that data, and I'm sorry, I don't really have raw data yet. So this is, again, very processed. But let me describe what I've done here. So I've taken one of the components of the CFT stress tensor, LNR processor, theta theta. The delta means that what I've done is I've taken it, and from the full TMU CFT, I could actually reconstruct what the TMU CFT would look like if it were hydrodynamic. So in other words, extract out an energy density, extract out the forward velocity, and then reconstruct term by term, ideal hydrodynamics, first order viscous correction, second order viscous correction, and so on. And what I've done is I've taken the difference between the numerical TMU CFT and the hydrodynamical guess, and then normalized it by the energy density. And here's what you find. And it's in line with what we saw in the quasi-normal modes study. It's very, even with second order viscous corrections, anyway, the thing is very close to hydrodynamical. So it's 1 in the 1%. So those black hole collisions, however, if you did the exact same procedure, what you find is this. So suddenly, look, you're in 20% discrepancy in the initially. So again, we're plotting the same quantity here. It's written out in a different way. So the two features I'd like to point out is at early times there's a large discrepancy modulo this initial time, which we could talk about if you'd like. And at late times it asymptotes to what we had seen before for the single black hole. And it's very easy to understand why, because with black hole collision, what's the result of a black hole collision? It's nothing but a perturbed single black hole. So you should expect to see exactly what we saw before. Are there any questions here? Oh, you should be asking what the gray thing is. So the point is, the dotted line is the numerical data of a given resolution. And the point in numerics is that one resolution won't give you the continuum data, but you can see the trends towards which your discretized solution is approaching the continuum solution. So what I've done here, so what you'll actually see as you plot different resolutions is that it's converging very nicely at second order in our case towards the continuum solution. What I've done here with the gray region is just showing you the region in which the continuum solution lies given that convergence. So in this case, it's the lower bound of the gray region. The continuum solution is.
Do you understand what these bumps do in the gray region, like I tried before?
Yeah, so you can see when you look at the resolution, the different resolution curves, why that is. It's just that the lower resolution turned out in this case was a little bit violent in that region, and it made the our error bars larger in that case. What actually happened in this case when we went to one higher resolution is that it went away. So it turned out that it's just a low resolution effect.
The TR that you get out of this, the final temperature of the black hole and the radius of the boundary sphere, what does that end up being?
For this simulation, I believe it's something like 2 times the radius of the sphere. So it's
actually really remarkable because, I mean, higher order corrections to hydrodynamics will involve Riemann tensors of the boundary sphere, which are not arbitrary, they're that small compared to ideal and medium viscous order things. It's remarkable.
What I haven't tried is,
again, when hydro is applicable and
exactly.
on the sphere is in the high temperature limit, this would be well within an intermediate temperature regime.
Yeah. So it comes back to your earlier question, actually. What would be nice to do, and I haven't done yet, is done a systematic study of different mass black hole collisions and see how things change. That would be interesting to see. Perhaps that might be the next thing, other than the other things I haven't. I unfortunately don't have an answer. That would be really interesting to see. I mean, is there something? Okay, so given the amount of time, let's just quickly go through the Poincare patch results. So what I want to point out here is that on the Poincare patch, there are 2 types of horizons we're interested in. There's the ones that were talked about yesterday a lot, which essentially are planar topology horizons. So here, I mean, it's planar in the sense that it covers the entire Poincare horizon. And there's the spherical type topology horizons that we'll also be interested in for these black hole collisions. So let me first show you what a planar type black hole simulation looks like. So what I've done here is, this is the scalar field. I've just sprayed an entire distribution of scalar field from infinity, negative infinity to infinity in this transverse direction. And I'm going to let this profile fall into the ball. So to orient you again, up here is the boundary, down here is the Poincare horizon, and the vertical direction is the z direction. So this is what happens. So as you can see, it just fell and promptly collapsed, and it formed a black hole that's rather large. The reason there's some asymmetry there is actually I designed, if you looked at the earlier emission data, so there's some non-trivial spatial dependence as well in the transverse direction. That's all that happens. You form a planar black hole, and this is somewhat more more or less like what happens in the shockwave collisions, except the shockwave collisions, what happens there is you have very localized distributions. But eventually, what those simulations rely on is that there's a planar black hole that's formed along with those shockwaves. Okay. Here's what the metric looks like. The reason I want to show this is there seemed to be a lot going on in that previous slide, mainly because it was a scalar field and it kept on getting eaten by the horizon. What I want to show you here is that it's rather quiescent actually, if you look at the metric. It just settles down. Okay, so now I'd like to show you what happens if you had a localized energy density distribution in the Poincare patch. So for example, now I don't have energy densities all throughout the transverse direction. Rather, it's localized. And in fact, this is a Gaussian in all directions. So, distributed. So what happens is that, well, if you made it strong enough, you'll form a black hole. And again, well, what's one way of thinking about these solutions? Well, remember, you have these spherical topology solutions in the global ADS. Try to think about what it looks like in the Poincare patch. And all it is it's a spherical topology horizon that falls towards the boundary. The falling, falls towards the Poincare horizon. And the falling is simply that the static ADS Schwarzschild in global ADS, from the point of view of the Poincare patch, is just exiting the slice.
In this case, where you have a localized lump of scalar, have you been able to find configurations that don't collapse into a spherical boundary?
Yes.
So have you studied the sort of boundary between these two as a function of the amplitude
Yes.
of the scalar to see if there's like Chopwick or something?
Yeah, we would like to. And in fact, my guess is it probably will be, because at the point
to compute the exponent, if that is true.
Exactly.
How that exponent compares.
Exactly. I mean, I wonder how good this intuition is, but I guess, like for the Chopwick scaling, it probably doesn't care that there's a cosmological constant there, because it's very.
That's what I want to know.
Yeah, it probably doesn't. We haven't done that study carefully. The main reason is that we're still working with the adaptive mesh refinement, but there you really have to get your adaptive mesh refinement very well tuned. In some sense, it's actually the perfect application of adaptive mesh refinement, the self-similar solutions that we expect. Yeah, so again, thanks for bringing this up, because I probably won't have time to talk about the other things that obviously we want to study, but we just don't have time right now because there's other things to do. That's one of them. Okay, so here's one of the transverse directions. Sorry, I didn't show you before, but I mean, all I want to show you there is it's nothing surprising. Okay, so the last set, now in the last 2 minutes or 1 minute, who knows how much I have, this just collision data. So this is going to be a very, it's going to be an underwhelming collision in the sense that we start from rest because we have time symmetric data. And so that means that these are not boosted at all. I've just made profiles like this so that I get the sort of horizons I want. So eventually what I want is, so my idea, and hopefully this will work, is instead of starting from rest, so I don't want to start from rest because it's too easy and too trivial in some sense. On the other hand, I don't want to solve the full binary black hole initial data problem because that's hard. So the idea I hope will work is that just instead stay with scalar field initial data, so the scalar field I'm displaying, but instead make the scalar field itself be boosted. And the idea hopefully is that those boosted scalar field profiles will collapse if it's strong enough, and it'll collapse to nothing but boosted black holes. So that's the end goal for this simulation. But right now it's just black holes at rest. They're strong enough such that the trapped surfaces are nearly touching, so you get a merger almost immediately. And you just have a large black hole that's falling down, and you might be distressed by the fact that my excision surface is growing. The reason for that is purely numerical. I have a rather large buffer here, and I'm still experimenting with what excision surface buffers are doing. Okay, so here's the metric. So again, like the obvious direction to go here might be to separate them further. What happens there, however, it turns out, is that these black holes that separate further will fall first before coming together, and because they're starting from rest. And that's a big waste of computational time, so that's why I'm thinking a boosted configuration would be better for what we want to do, instead of waiting for these things to fall and talk to each other and finally merge. Okay, so here's, in the last few minutes, just a few visualizations here of, okay, we don't want to see that. A few visualizations of like the raw TMU CFT for that configuration. So this is TT. So again, this is the boundary. So this is the beamline direction. You can interpret it like that. And this direction should go from -infinity to infinity too. But remember, for these head-on collisions, we're doing an SO2 symmetry. So think of this and then just rotate it around. That's the full solution. Okay, so we start with two lumps of energy density, roughly corresponding to the shadows of the black hole on the boundary. And we let that evolve for the time that we had. It just comes together and it goes outwards. It's pretty much what you expect, in fact. And it's very much in line with what we saw before in the energy density of the other simulations on the boundary. But it would be, what we're pushing for right now is to make that time larger and to make the initial separation larger, and hopefully to get boosted initial data initially too.
So your energy is actually pretty negative, right? I mean, it's almost as negative as the positive part.
Yes. So this is TT, the TT component. If you want the energy density, the real energy density, it's going to be some combination of these, of the metric components. So it's going to be TT, I think, plus, I can't remember the exact expression.
It's just Minkowski space, right?
Oh, I see what you mean. Yeah, so I suppose it would be. Yeah, that's right. It probably should be the same. So the reason I say that is what I think of as energy density is, the energy density you would associate with hydrodynamic evolution, for example. And in general, what you need to do there is you take the TMU CFT, diagonalize it, and then, figure out what the eigenvalues are. And the one associated with the time-lapse one is what I call energy density. But maybe you're right. It might be exactly the same.
For sure, the origin is the same as symmetry.
Yeah.
There, also there is.
You could make a plot that's a subset of the space where you could find such a such a velocity for which the...
That's right.
Because it seems like you just started on a lot of energy and now you're relatively relaxed. For hydrodynamics, you would never expect to find these negative energy densities.
Yeah.
So
I suppose,
yeah. Describe hydrodynamics in some sense.
This is what he's saying. To understand that, you would need to reconstruct the velocity vector. And within that little rest frame that you would measure.
So you're not
see that you have a positive or negative.
Because they started rest, right? So the velocities cannot be too dramatic, or are they?
Yeah, so we haven't plotted what the velocities are, but presumably they will speed up at some point. And what we've seen in previous black hole simulations is that they get pretty large very quickly.
Even if you boost, then you would never get TTT negative in hydrodynamics.
Yeah, that's probably right. But I thought what the problem is, what I don't yet have is, as you said, just, first of all, I don't have, high resolutions to see what the convergence trends are. It could be that this is just a resolution issue. But on the other hand, what I'd really like to do is look at the epsilon, the energy density that's associated with the time-like Killing vector, the time-like U mu.
Wasn't this, along these lines, didn't Paul have a paper along these lines showing that for certain black hole collisions that seemed to be rule that you could reconstruct the effective hydrodynamic description from a subset of the...
Yeah, I was on it there.
No, okay, then isn't that this?
Well, this is really outside regime where hydrodynamics is applicable, so I would expect an even first of all in hydrodynamics, and secondly, the energy density is still very negative. Mine's 2.2 and the positive part is 3.6. But anyway,
Actually, what I forget is what should we, but I guess so it's ordered unity. Yeah, you're right, it's fairly large, 20% of the original. Yeah.
Did you compare for the simulations how the team you knew and the team you know hydro compare? Like
No, not yet. So these are the things that we need to, because those would be the consistency checks that would show whether this is to be believed or not. These are just the initial raw data that I have to show that's literally corresponding to the previous collision that I just showed you.
Is there energy actually conserved?
Yeah, that's a good question to ask. But again, unless we did something, it probably is in the sense that it's it's just a consequence of the field equations. But again, we should see convergence strengths first, make sure. And that'll give us some idea of how far we are from the continuum solution.
Should probably wrap up this.
Are we over a lot?
Yeah.
Okay, so let's stop here. Thank you.
Thank you. And I suggest to discuss more over the next 10 minutes over the break and then get ourselves back on track.